Welcome to qnawire.
So at the inlet, we have the Mach number, which is Ma1 here, is equal to V1 over C1. V1 is the velocity of nitrogen at the inlet, and C1 here is the speed of sound at the inlet. So when the C1 can be expressed as a square root KRT1. So therefore, we have V1 over square root KRT1 is the Mach number in this case. So we know the inlet velocity is given as 100 meters per second. If you take a look at a table for the ideal gas specific heat of various common gases. So the specific heat ratio for the nitrogen gas should be 1.4, and the gas constant for the nitrogen gas is 0.2968 kilojoule per kilogram times Kelvin, which is 296.8 joule per kilogram times Kelvin. And we know the inlet temperature is 10 degrees Celsius, which is 283 Kelvin. So now let's plug in back to the equation to determine the Mach number. So the Mach number is equal to 100 meter per second over square root 1.4 and then times 296.8 joule per kilogram times Kelvin and then times 283 Kelvin. And this will give us the Mach number at the inlets is about 0.2916. So now let's take a look at the Mach number at the axis. So at the axis, we know the Mach number can be equal to V2 over C2, which is V2 over square root KRT2. V2 is the exit velocity, and T2 is the exit temperature. So we know the heat transfer was here, Q here can be equal to Cp times T2 minus T1 plus V2 squared minus V1 squared over 2. If we do some arrangement here, eventually we have T2, which is the outlet temperature, is equal to T1 plus 2Q plus V1 squared minus V2 squared over 2 Cp. So we know the heat transfer is given as 120 kilojoule per kilograms. And if you take a look at the table for the ideal gas specific heat of various common gases, the specific heat for the nitrogen gas at a constant pressure is 1.039 kilojoule per kilogram times Kelvin. So now we can determine the temperature at the axis. So as you can tell, I make the conversion here, which is making conversion from meter square per second square to kilojoule per kilograms. So the reason why I did that because, as you can tell, the values above the denominator here is having a units kilojoule per kilograms. So therefore, in order to organize the whole equation, I have to convert the meter per second to the power 2 to the kilojoule per kilograms, which is about 1,000 here, okay? Because 1 kilojoule per kilograms is equal to 1,000 meters square per second square. So eventually this will give us the exit temperature is about 384 Kelvin. So now we can determine the Mach number at the axis, which is equal to 200 meter per second over square root 1.400 times 269.8 joule per kilogram times Kelvin, and then times the outlet temperature, which is 384 Kelvin. And this will give us the Mach number in this case is about 0.501. And these are the answers for this question.